Hello, this is Dr. Strickland. In this video, we will continue our investigation of the Diels-Alder reaction. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the more difficult things we will do together in class. Now, so far with our Diels-Alder reaction, we have dealt with situations where both the conjugated diene and the dienophile were symmetrical, or where one was symmetrical and one was not. When both of them are unsymmetrical, then the two pieces have a choice about how they line up relative to each other. And because of that, you get two possible constitutional isomers. That's a regioselective reaction. And so what we're going to do is walk through this analysis to figure out which one should be the major product. Now, just to remind you, a dienophile is going to either be an alkene or an alkyne. And so if you draw an imaginary line through the double or triple bond that joins those two carbons, you can check and see if one side looks the same as the other side. If they do, it's symmetrical. If they don't, it's unsymmetrical, like in this case. An unsymmetrical diene or an unsymmetrical conjugated diene, you need to look in a different place. You're going to draw this imaginary line through the sigma bond that joins those two internal carbons of the conjugated system. And again, if one side looks like the other, it's symmetrical. And if they don't, like in this case, then it's unsymmetrical. But you can determine what the orientation of one relative to the other needs to be by looking at the other major resonance contributor. So with the conjugated diene, we've got a substituent on here that is an electron donating substituent. So I'm going to just draw all the way to the other end of the conjugated system. And when I do that, of course, you remember the atoms are all in exactly the same places. None of the atoms ever move when you have a resonance contributor, but electrons move. All right, so we've got one more pair of electrons. So this pair of electrons went from being a non-bonding pair to being a pi bond. This pi bond swings around to become a pi bond here between the two internal carbons of the conjugated system, and this pi bond becomes a non-bonding pair there. So we've got a positive charge here and a negative charge there. All right, if we go over here to the dienophile, we've got 4 sp2 atoms in a row. We're going to go towards the one that has the higher electronegativity. So that means we're going up like this. And then the resonance contributor that we've made then looks like this. Atoms all in the same places again. But so this one, this pi bond swings around to become a pi bond there. This pair of electrons comes up to become a new non-bonding pair of electrons. We know that has a negative charge. This carbon has an incomplete octet. So we're looking for the two atoms on the end of the diene and the dienophile that have opposite charges. So in that case, it's this one and this one. And so what that tells me is that the correct orientation will look like this. So now I'm just going to go back to the structures that I started with the conjugated diene in its S-cis conformation, and then the dienophile just lined up right next to it. And you can either include that hydrogen or not. All right. So, and that leads to this one. So this is the major problem. But you would only know that by going through this analysis to find where the charges are on the carbons that will be involved in the Diels-Alder reaction. Okay, So let's take a little bit of a look at the stereochemistry that's involved. Since the Diels-Alder reaction is a syn addition, it's stereoselective. One of the questions we're going to look at is it also stereospecific? Because I've got here, I've got a cis dienophile and I've got a trans dienophile. So I've got two different alkenes that are reacting with the same conjugated diene. And so what I want to know is, if we have the syn addition in both cases, do we make the same stereoisomers in both cases? So if you do the electron movement, and since a Diels-Alder reaction only has one step, you can all the time just do the curved arrows if you want to. You don't have to, but it just helps me to keep my place. Oops, sorry, right there. Okay, so what did we make? Well, we made that new 6-membered ring. And it has that pi bond that's there between the two internal carbons of that conjugated diene. Let's put the color codes back in. Okay, so these are the internal carbons of the conjugated diene. These are the external ones. And then the two dienophile carbons that are involved are right there. And the two new bonds, of course, are right here. All right, so what else was attached to these two carbons of the dienophile? Well, this one has a methyl ketone and a hydrogen, and this one has a methyl group and a hydrogen. When you get the syn addition, this piece is either going to come and hover over the diene or go under it. So if it goes over it, then that means that these two things on the right will be pushed up. So we've got this and this going up. Now you can draw the hydrogens in if you wish, and they would just be on down bonds. The other possibility is that the dienophile approaches the diene from underneath. And in that case, the stereoisomer of the product looks like this, where those two pieces on the right that we were looking at will now be on down bonds, and hydrogens would be on up bonds. All right, so if we do the trans counterpart, you know that both of them are going to start like this. The question is, where did these guys go? So I want you to put them into both of these two stereoisomers, and then take a look at this and tell me if this reaction is stereospecific or not. So pause the video and do those things, and then come on back. All right, welcome back. So the way we were doing this was, if we had something on the right, it would go to an up bond, and something on the left would go to a down bond if the dienophile approaches from the top. So that means that if it approaches from the top, the ketone will be on an up bond, but the methyl group will be on a down bond. Conversely, if the dienophile approaches from below this paper, then this guy will be a down bond, and this guy will be an up bond. Okay, so these are the stereoisomers produced from this reaction, and the question is, did the cis one make the same stereoisomers as a trans one? And the answer is no. And that means that this reaction is not only stereoselective, it's also stereospecific. All right, right off the page. There we go. All right. So one more thing I want to talk about, and that is, if you have a target that you want to make, how do you figure out what the diene and dienophile would have to have been? So I'm going to use that open arrow to say, if I'm walking backward one step, what was the diene and what was the dienophile? Basically, we're taking it apart, knowing that the two new bonds that were formed were between the orange ones and the yellow ones, right? These are the atoms that came from our conjugated diene. These are the atoms that came from our dienophile. So we'll just back that out, and that tells me that the conjugated diene must have been 1,3-butadiene, and the dienophile must have been this guy, 2-cyclohexenone. Now this one is there's a little more to it, and you'll see this in your textbook. If you've got this little piece sticking up, then that belongs to either the diene or the dienophile. And let's just have the diene come from the left side, and that would mean that the two carbons that get involved in the new carbon-carbon double bond are the internal carbons of the conjugated system, and then the two just adjacent to them were the outside, and that would mean that these two came from the dienophile. Now that tells me several things. For one thing, this carbon is just along for the ride, and this was a cyclic diene. And I'm gonna color these in so you can see that the carbon that just sticks out, that forms a bridge here, is just this one right there. Also, if your two carbons from the dienophiles still have a pi bond between them, that means that this was a triple bond, not a double bond. See that? All right. So that is the basic story about the stereochemistry of the Diels-Alder reaction. If you have any questions, please send them to me.